Greetings to all. In last video, we have discussed about a concept called slip and its effect on rotor parameter in running a condition. With that continuation, now we are going to discuss about equivalent circuit of three-phase induction motor. We are having two types. One is exact equivalent circuit, that is called actual equivalent circuit, and second one is called approximate equivalent circuit, and both these circuits are having its own purposes. The very first circuit is required for obtaining exact torque being developed on the rotor, and whereas the approximate equivalent circuit is required for obtaining a performance characteristics of various parameters while conducting tests like no load and blocked rotor test on three-phase induction motor. And we can make use of this approximate equivalent circuit even at the time of drawing circle or diagram. So in general, the purpose of having equivalent circuit for any electrical machine, either it may be of static or rotating electrical machine, is to get the performance characteristics of various parameters at steady state condition. So this is the purpose of having equivalent circuit. So here in induction motor 2, we are going to obtain various parameters behavior under steady state condition. So for that, we are going to make use of equivalent circuit of transformer, because we used to call induction motor as a rotating transformer. So on that note, we are going to have a short recall on equivalent circuit of a transformer. In transformer, we are having primary and secondary winding being connected on a common magnetic core, and for indicating the presence of winding impedance, we are having R1, X1. Likewise, in secondary, R2, X2. Primary is connected with supply and secondary is connected with a load. And for the very first operation for electrical machine is the creation of flux. It means we have to maintain some constant flux within the machine to have an operation smoothly. So here the contribution of flux creation is indicated by a component called X0, and the current required for creation of flux is Im, that is magnetizing current. And we used to have so many losses in a machine, especially three losses, and we can categorize those three losses into fixed on variable losses. That fixed, that is constant loss, cannot eradicate completely from a machine by any means, so that loss is going to consume a real power. So because of that real power consumption, we are indicating the presence of constant loss by R0, and the current flowing to that R0 is IW, that is working current. It means it is going to have a supply to the losses, and whereas magnetizing current is required for sustaining flux in the core. And these two currents came from a current called I0, that is no load current. We can say I0 is resolved into two components. One is IW and another one is IM. So we can call this IW as an active component and IM as a reactive component. And I0 is a portion of I1. Only there is a flow of current on the primary, then only we used to have a flow of I0 on a machine. So now we will start with the operation of transformer. Once the supply is connected with primary winding, there will be a flow of current called I1, and I1 contains the current called I0, and I0 is resolving into two components, and because of Im there will be a creation of flux, and that flux is called psi. And we know due to mutual inductance, this creation of flux on the primary coil is going to link with the secondary coil. So this is because of that mutual inductance. And due to a leakage flux happening in the primary, so we can call that as a self-inductance. We used to have a EMF inducement on the primary coil 2. So we can have a EMF inducement on the primary as E1 and secondary as E2. E1 is due to self-inductance and E2 is due to mutual inductance. And the main reason is the creation of flux due to Im flowing to X0. And this secondary winding is having a closed path, And we all know if there is a flow of current or an EMF inducement in any closed circuit, that EMF inducement is going to follow Lenz's law. It means it is going to oppose the sign of the main cause, that is supply. So supply is having minus and plus. So it is going to oppose the sign, that is polarity of the supply. So we can have a polarity for EMF inducement as well as load like plus and minus. It is obeying Lenz's law. So now again, due to a closed path on the secondary coil, we are having a flow of current called I2 on the secondary coil. And again, due to a flow of current on the secondary coil, again there will be a creation of flux on the secondary coil, and that flux is called psi dash. And we know again by using Lenz's law, this psi dash is going to oppose the direction of main flux, that is primary flux. And we can say we are having a cancellation of flux on the core, and that cancellation of flux we are calling that as a demagnetizing effect. That demagnetizing effect is going to make a reduction in the main flux, and that reduction in main flux is not an entertaining, because we cannot encourage that reduction in flux, because we have to maintain some constant flux in the stator core. So for again we have to increase, it means we can have to maintain the constant flux. So for increasing the constant flux, we are going to get extra current from the main supply. So that drawing of extra current from the main supply is for overcoming the demagnetizing effect happening due to the flow of current I2 on the secondary coil. So we can call that extra current only because of the flow of I2. Because of I2 only we had psi dash, and this psi dash is reducing the main flux, but we required constant main flux, and for again boosting up that main flux we are having extra current from the primary coil, and that extra current is because of I2. So in order to indicating the reason for the extra current, we are naming that current as I2 dash, and we are going to have a value as K into I2. K is nothing but a turns ratio of a transformer. Here we are having a turns ratio, that is N2 by N1 is the turns ratio for a transformer, and here we are going to have some changes in the turns ratio for induction motor. Now we'll discuss that later. So this is the operation of a equivalent circuit in the transformer. So now we are going to compare, or we are going to extract equivalent circuit for induction motor from this transformer. So here I think all the operation for the transformer is almost clear now. So now we'll move on to the stator model of induction motor. So we can compare the primary winding of transformer with the stator of induction motor, because we are not having any much changes on the stator. So we can directly take the primary winding model as a stator model for induction motor. In primary we are having stator field winding. So we are having stator field windings impedance R1 X1, constant loss, creation of RMF, rotating magnetic field. So here main supply, stator supply is V1 and stator current is I1. Here we are drawing that equivalent circuit per phase. Even though we are having a 3-phase, here it is an equivalent circuit for per phase, and due to a creation of flux, there will be an EMF inducement on the stator. So that EMF inducement on the stator is called E1. Now we'll move on to the rotor model. For designing a rotor, for understanding the analysis or understanding the behavior of the rotor, we have to consider two conditions. One is standstill and another one is running a condition. So in a standstill, we all know it is going to behave just like a stator. So in transformer we used to have secondary winding being connected with load. So the same behavior here we can observe at the standstill condition for a rotor in a 3-phase induction motor. Now we are coming to the running condition of 3-phase induction motor. We know in running condition all the rotor parameters is going to have a dependency on the slip value. So induced EMF as SE2, flow of current as SI2, and the resistance is same for both standstill and running condition, and X2 will become SX2. So this is the equivalent model of rotor at a running condition. So we can say this model is having its own frequency. We can call this frequency as a rotor frequency, and we know the formula of rotor frequency is S times the supply frequency. And for combining the stator and rotor model together in an equivalent circuit, we have to convert this rotor frequency to a stator frequency. So for that, now we can write the current flow, that is current equation as SE2 divided by Z, and we are going to change this rotor frequency equation to a stator frequency equation. So here rearrange the value of slip over here, and according to this equation we are going to redraw this rotor model. So here we are having E2, instead of SE2 we are having E2, and instead of R2 we are having R2 by S, and SX2 will become X2. So we can say this model is now operating at a frequency called F, that is a stator frequency. So now we have changed the frequency from rotor to a stator frequency. And now for indicating the presence of rotor conductor, we used to have R2, X2 separately. So here we are having R2 by S. We know the value of R2 both at standstill and running condition. It's simply R2. But here we are having R2 by S. So we have to rearrange the presence of R2 separately, and for that we are going to consider that R2 by S, and we are going to write this equation by adding and subtracting the value called R2. And after rearranging this equation, we can write this equation as R2 plus 1 by S minus 1 R2, and we have separated the winding resistance. So with the help of this equation, again we can redraw this equivalent rotor model, and E2, and here we are having R2 and winding reactance X2, and the flow of current is I2, and this extra term, that is 1 by S minus 1, we can write this as a 1 minus S by S, and this indicating the presence of load, that is mechanical load. In motor we used to have a mechanical load, but here we can call this as a electrical equivalent of mechanical load. It is an electrical equivalent of mechanical load. So we can consider this as an final equivalent of rotor model. So now we are having stator and rotor model, and now we are going to combine these two, just like a generalized transformer model. So in transformer we had primary and secondary winding, and likewise here we are having a stator and a rotor model. In rotor we are having this equivalent, electrical equivalent of mechanical load, and we used to call this mechanical load as a net mechanical load. We used to have gross mechanical and net mechanical load, and the reason is, if we are not going to include mechanical loss, we can call this as a net mechanical load, or if you are going to include mechanical loss on the rotor side, that mechanical power will become a cross mechanical power. And here we are having a constant loss, that is constant loss is occurring due to a presence of iron and mechanical power, and due to a mechanical power developed, we are having a mechanical loss, and this mechanical loss is present at the stator side, not on the rotor. It means we have removed the mechanical loss happening on the rotor side, and that removal of rotor side, and now we are indicating that electrical equivalent of mechanical output as net mechanical output. If suppose if you are going to include the presence of mechanical losses on the rotor side, and that time we have to represent that mechanical output as gross mechanical output. So that's the difference between gross and net mechanical output. So now again we have to consider the turns ratio for induction motor. Whereas in transformer the turns ratio is called K, and the value is being represented in terms of N2 by N1. But whereas here we are calling that as a effective turns on stator and effective turns on rotor. Simply in transformer we calling that as a number of turns on the primary and secondary. But whereas in induction motor we are calling the same number of turns as a effective number of turns on the stator and effective number of turns on the rotor. Why we are calling that as a effective? Means we know the EMF creation, that is inducement on any AC circuit, is 4.44 frequency amount of flux and then the number of turns. And here especially at the rotating machine we have to consider the winding factor also, because we are having the arrangement of the winding on the core, so that we are having an extra term called winding factor on both rotor as well as on stator. So the combination of number of turns and the winding factor, we are calling that as a effective turns. So that's the reason for indicating the number of turns as effective turns on stator as well as on the rotor. So we have combined the stator and rotor model. It is just like looking like a transformer. So we can call this equivalent circuit as a generalized transformer model. Now we are going to combine these two windings. So we can remove the the core linkage. So after removing the core linkage, we are bringing the rotor side to a stator, so that we are naming that circuit as a referred to stator. So once if we are bringing that rotor parameters to a stator, we have to represent that rotor parameters by using a prime, that is R2 dash, X2 dash, I2 dash, E2 dash and R2 dash, like that. So here it is more or less the same, we have removed that flux linkage, that's all, and we are replacing the parameter naming as R2 prime, X2 prime, it indicating the combination of rotor to a stator. So this is the actual equivalent circuit. We are calling that as exact equivalent circuit, and here the value of E2 dash is nothing but E2 by K, because we are referring the rotor to a stator. So we have to include the number of turns we have had on at the time of flux linkage. Here in this diagram we are having a flux linkage, and it is having number of turns, that is we are having a turns ratio, and so we have to include that turns ratio while we are going to remove this flux linkage. It means, well, at the time of combining stator and rotor and at the time of removing this flux linkage, we have to include this turns ratio with the parameter. So here we are having a reference of rotor to a stator. So we can write this E2 dash as E2 by K and R2 dash as R2 by K square. We know for the active sources we have to use turns ratio as K, and for the passive element we have to use the turns ratio as K square. And the turns ratio is here, the value is effective turns on the rotor by effective turns on the stator. In transformer we used to write that turns ratio as N2 by N1, and here we are writing that as instead of 2 and 1 we are having a rotor and a stator. So that's all. And now we are going to rearrange the equivalent circuit by including losses on its corresponding place. It means that mechanical loss will never happen at the stator. It happen only if there is a creation of power, that is only there is a mechanical power developed on the rotor, at the time only we can have a mechanical loss. So we are going to bring that mechanical loss to a rotor side. So for that we have removed this RC component on the stator, and until now we are having a net mechanical power, and because of that inclusion of rotor loss on the rotor side, we can call that mechanical output as a gross mechanical output. So we can understand the name for mechanical power as net and gross. If you are not including loss, we can call that as a net, and if you are including, that power will become gross mechanical power. So this is the final exact equivalent model of three-phase induction motor. And now we'll see the second type of equivalent circuit, and from the name itself we can say it is an approximate. It means we are going to do some approximation, that is adjustment on the equivalent circuit, actual equivalent and circuit. It means we are going to combine all the winding parameters. It means both on stator and rotor we are going to combine all the parameters. So we are having this, we are rearranging the loss component and winding component. We can say this loss component as a shunt parameter and this as a series parameter. It means we are rearranging, it means we are combining all these series parameters together and shunt parameter together. So this is what happening in the approximate equivalent circuit. And what are the disadvantages we are having this approximate equivalent circuit is we are not considering the no load stator impedance drop and no load stator copper loss, and because of that not consideration of no load, and we used to have the flow of current, that is IW and IM, that is shunt branch currents are more than the actual value, and because of that we used to have a overestimation of this iron and mechanical loss. That is, we are used to have a minimum acceptable constant loss in a machine, but at the time of approximating this equivalent circuit and due to bringing the shunt parameter immediately next to the supply, we are having overestimation of the mechanical and iron losses. And what is meant by a no load stator impedance and copper loss? Because here, as I said earlier, that primary current is going to have some portion of I0. That primary current is having I0, and in the previous case here we can say that I0 is flowing after the I1 is coming next to R1 and X2. It means I0 here, the I1 is having I0, and you can say this I0 is flowing through R1 and X1 in exact equivalent circuit. It means this R1 and X1 is going to have an impedance drop. It is going to have its own loss like copper loss and the voltage loss, that is impedance loss and copper loss, and these two losses happening because of the flow of current through it. Simply we may call that current as I1, but this I1 is containing I0 too. So this I0 also is going to have an impact on R1 and X1 initially, but whereas in approximate equivalent circuit, this I0 also contained in I1, but it means I1 is having I0, but this I0 is not going to have any effect on R1 and X1. So we can say in exact equivalent circuit, I0 is having effect on the stator parameter, and whereas in approximate equivalent circuit, this I0 is not having any effect on the stator parameter. So because of that, we are not having any losses on the stator parameter due to no load current. So because of that, we are having a more overestimation of the mechanical losses. So these are all the disadvantages of approximate equivalent circuit. And even though we are having these disadvantages, we are making use of this approximate equivalent circuit for understanding the performance behavior of various parameters while doing no load test and blocked rotor test. So until now we have discussed about the equivalent circuit of three-phase induction motor. We have compared that with equivalent circuit of transformer. So from primary of transformer we have obtained stator for three-phase induction motor, and for obtaining the equivalent model of rotor we have discussed two conditions. One is standstill and another one is running condition. In running condition we used to have a rotor frequency, that is S times our supply frequency, and for combining stator and rotor model together we have to convert that rotor frequency to a stator frequency, and at the time of converting a rotor frequency to a stator frequency we are going to include the electrical equivalent of mechanical load, and we used to represent that electrical equivalent of mechanical load either as gross or net mechanical output. And if you are going to include mechanical losses on the rotor side, that time we can call that mechanical power as gross mechanical power, or if you are going to remove the mechanical losses from the rotor circuit, and that mechanical power is called net mechanical power. And we have discussed about the number of turns available on the induction machine, whereas in transformer we used to represent that as a number of turns on the primary and secondary, and here we have to include the winding factor on the stator as well as on the rotor. So we are calling the number of turns on the induction machine as effective number of turns on the stator as well as effective number of turns on the rotor. And for drawing the approximate equivalent circuit we are going to segregate. It means we are going to rearrange the shunt and series branch parameters. First is shunt, and next we are going to combine all the series parameters together. And we used to have several disadvantages in the approximate equivalent circuit, even though we are using for obtaining parameters for no load and blocker rotor test. Especially at the time of drawing circle diagram we are using this approximate equivalent and circuit. And that's all about equivalent circuit of three-phase induction motor. Thank you.